We're in Belgium, in a factory specialising in dyeing fabrics. Every year, around 12,000 kilometres of textile materials are dyed here. And for that, millions of litres of water are needed. After use, this water is full of colorants, chemicals and salts. How to recycle this polluted water in an efficient and affordable way so it can be reused in the whole dyeing process? European researchers think they've found an answer to this question.
Assalamualaikum and good day. It is honored to be here today and present my research study for 2nd International Science and Technology Colloquium. My name is Umi Madina from Faculty of Applied Science UITM Police Branch, and my research study entitled Structural Properties of Silver Carbonate Cadmium Sulfide for Enhanced Photocatalytic Degradation towards the Methyl Orange. UNESCO has mentioned in the International for Water Quality that limited sources of clean water result from large amount of untreated or inadequately treated wastewater that has been released to the water stream. Among the various contaminants, dyes and heavy metals are the most persistent in the water, and their complex structure cause to the biodegradable problem. Dyes such as methyl orange are the most popular and extensively used in dyeing and textile industries. Methyl orange is an ionic azo dye and a part of xenobiotic characteristic that can possess to the major ecological impact even at low concentration. It also has a complex aromatic structure which is non-biodegradable. As a consequence, photocatalysis is a new technology that has been studied by many researchers to encounter this issue. What is photocatalysis and how it works? Photocatalysis is an advanced oxidation process that involves acceleration of a chemical reaction by the photocatalyst. When light being penetrated into the semiconductor, it will excite the electron from the valence band to the conduction band. Thus, this electron react with the oxygen while the hole react with the water, leads to the formation of spore oxide radicals and hydroxide radicals. So these radicals help to degrade methyl orange or other model pollutant to become carbon dioxide and water. Among the various photocatalysts, silver carbonate is a high potential photocatalyst and it is silver azo material. Silver carbonate has a narrow band gap energy approximately 2.32 electron volt, which lead to the strong oxidation photocatalyst and excellent towards the visible light. However, it has some limitation, which lead to the problem where silver carbonate has a low photoinduced electron, which will interfere the efficiency of photocatalytic degradation of model pollutant. Besides that, cadmium sulfide also has been reported act as a good photocatalyst for wastewater treatment with appropriate narrow band gap energy around 2.4 electron volt. This allows for cadmium sulfide has a great solar absorption, thus able to improve the photogenerated electron hole pair and undergo redox reaction process. But cadmium sulfide photocatalyst is less stability due to the photocorrosion phenomenon. It is possible to be happen when sulfur ions are attacked by photogenerated hole and oxidized into elemental sulfur, cause anodic corrosion. The problem of photocorrosion towards the silver carbonate and cadmium sulfide can be solved by combining two semiconductors to construct the heterojunction, which help to remain the redox potential ability for the efficient photodegradation of methyl orange. As illustrated in this slide, shown how cadmium sulfide was synthesized. Cadmium sulfide was synthesized by chemical precipitation method, where the addition of cadmium chloride and sodium sulfide as the precursor. Along with that, with the ratio 50-50 distilled water and ethanol was added and stirred until it homogeneous around 4 hours. Then, the sample was centrifuged and dried for overnight to obtain the orange to yellowish sample. As the completion synthesis of parents and composite catalysts, the preparation of a coupling semiconductor was shown details in this slide. This nanocomposite of silver carbonate cadmium sulfide were prepared with a facile precipitation at different ratio 95:5, 90:10 and 85:15 to explore the optimum of modified photocatalyst for higher photocatalytic activity. As the completion synthesis of parents and composite catalysts, the preparation of a coupling semiconductor was shown details in this slide. This nanocomposite of silver carbonate cadmium sulfide were prepared with a facile precipitation at different ratio 95:5, 90:10 and 85:15 to explore the optimum of modified photocatalyst for higher photocatalytic activity. In this section, photocatalytic degradation of methyl orange was undergo as the schematic diagram in the slide. This analysis was running for 1 hour with 15-minute interval. 3 ml of a dye was took to check the absorbance. To analyze the percent remaining, it was calculated as stated formula by difference between the final absorbance and initial absorbance of methyl orange. The SRD defectogram of synthesized silver carbonate, cadmium sulfide and modified photocatalyst with a various ratio of composite cadmium sulfide 5%, 10% and 15% are depicted in figure 1. The pure silver carbonate display the characteristic diffraction peak at 2 theta angle, which index to JCPDS 26-20339 as monoclinic phase. In addition, cadmium sulfide exhibit well-defined peak at JCPDS 41-21049 as it is being enlarged in figure 1b. The defectogram of all catalysts is the same with slightly decreased intensity after increasing the cadmium sulfide loading on the silver carbonate. Figure 1 also shows that the peaks of cadmium sulfide are not visible in the modified photocatalyst ACD, leaving the silver carbonate peaks only. The peaks of cadmium sulfide less intense and may not detected due to the lower concentration of cadmium sulfide that has been composited into the silver carbonate. FTIR analysis was reported to analyze the functional group and surface characteristics present in the sample as illustrated in the figure 2. The spectral pattern for the silver carbonate exhibit absorption band of carbonate ion CO32- at the peak of 1340 and 835 cm-1. The band at 622 cm-1 correspond to the CDS stretching band, which indicates it was successfully synthesized, but due to the lower concentration that were added into the silver carbonate, the intensity of cadmium sulfide peak was less intangible for the modified photocatalyst 5-ACD, 10-ACD and 15-ACD. In addition, the band at 3321 cm-1 attributed to the bending vibration of OH because the absorbed water on the surface cadmium sulfide. When increase of composite material, the cadmium sulfide towards the silver carbonate, it clearly showed that the peak of a carbonate ion getting less intense compared to the pure catalyst, which is silver carbonate. In order to characterize the surface morphology and elemental composition, FISM analysis was performed on the silver carbonate, cadmium sulfide and 10-ACD. Figure 3a displays that the synthesized silver carbonate exhibit different size of rod-like particle with a smooth surface at the average about 2 micrometer. In contrast, cadmium sulfide are uniformly distributed with a flower-like structure shown in the figure 3b. Figure 3c demonstrates that the structure remains rod-like and the structure of cadmium sulfide not visible when cadmium sulfide is deposited on the surface of a silver carbonate. This is due to the lower amount of cadmium sulfide that has been used. This also affirms that all the elements are strongly present and successfully deposited, including cadmium, sulfur with the silver carbonate. Based on 3C, show that the element of cadmium and sulfur are well distributed on the rod-like particle of silver carbonate, which give a strong contact between silver carbonate and cadmium sulfide that predict more harvesting of visible light during the photocatalytic degradation. The photocatalytic activity of all prepared sample was investigated in the visible light-driven degradation of methyl orange for 60 minutes, and the results are illustrated in the figure 4. It can be seen that 10-ACD has the highest photodegradation, which is 0.0355 minute -1, followed by 5-ACD 0.0252 minute -1 and 15-ACD with the 0.0217 minute -1. The modified of 10-ACD photocatalyst exhibit a strong attraction between silver carbonate and cadmium sulfide, resulting in a light harvesting ability, leads to the significant increase in the efficiency of methyl orange photodegradation. It can conclude that the fabrication of a composite photocatalyst between silver carbonate and cadmium sulfide is successfully developed using the facile chemical precipitation method. The optimum ratio for the photocatalytic degradation was found at the 10-ACD, and the degradation of methyl orange achieved a maximum of 95.94%. The enhanced photocatalysis has excellent photocatalytic performance, is cost-effective and environmentally sustainable. In this view, it can apply to treat the organic pollutant or dye in most wastewater industries.